All right, we're starting chapter 10 today. So, oh, let me, okay, that, okay. So we're starting chapter 10 today. So this week is chapter 10, which means that next week on Monday is our next test. So it will be chapters 9, 10, and then the IR analysis stuff. So a little bit of chapter 14. I will get you a study guide soon. I did post a couple things over the weekend. I posted a hyperdoc. So Ryan West, one of my former students, she does a lot of SI classes. She made it for us. So it's essentially a study tool, but it links out to a lot of other resources. And if you, it's a collaborative document. So whatever you write on it will be seen by anybody else that sees it. But it's a way for us, or a way for you to kind of work on stuff, but kind of see what other people are doing. So feel free to use it. It's a really cool study tool. She's trying it out in a handful of classes, and I told her she could make one for us. And then I saw a post on Instagram about like end of semester stress and end of semester burnout, and it had a handful of ideas, and I just thought it was a good list. So I turned it into a PDF and made each idea into a link with like either how to accomplish that or why it's important. So that's up there as well in an announcement. I think that's all. I feel like there might have been something else, but I think that's it. So test, and then we will do chapters 12 and 13, kind of 11, but 11's weird, so we'll talk about that next week. And then we're done. It's very quickly coming to an end. Okay, chapter 10. Chapter 10 is called Radical Reactions. So we are going to look at some of the reactions from previous chapters that I said, we're not going to talk about that quite yet. And the reason why we didn't talk about them before is because they didn't fit the pattern of that alkene chapter or the alkyne chapter, but they will fit in with this current one. So we do have to talk about what radicals are, and here's kind of the unfortunate thing. They don't follow those patterns that we learned back in chapter, I want to say chapter 6, chapter 5, whatever chapter we learned about just the 4 basic mechanism patterns. Radicals have their own patterns, and you're really not going to see them outside of this chapter. We might reference them when we're using a catalyst, in the fall semester, or you might hear about them when you take inorganic chemistry if you need to. But for the most part, they're pretty well contained within this chapter. And it's a rare thing that I'm able to say that for our class, because you've probably noticed, you've seen how well everything kind of mushes together. And this is one of those little island chapters, a little standalone chapter. All right. We're starting by looking at what a radical is and how those bonds break. So a radical is an unpaired electron. It's not stable. Electrons like to be paired up. So when an electron is unpaired, it's not stable. That means that it wants to react with something else so that it can get paired up. The way that they form is through a homolytic bond cleavage. So that's what's shown right here. We talked about homolytic and heterolytic bond breakage, probably back in chapter 6 also. But if we look at, let's see, let me put it right here. If we do this, and then we get a cation and an anion, that is a heterolytic bond cleavage. So hetero we know means different, and so it's hetero, or it's different, because each atom is getting something different, meaning the X is going to have a positive charge and it didn't get any of the electrons. The Y gets both of the electrons and now it has a negative charge. So they end up in different scenarios, different situations, hetero. With the homolytic bond cleavage, we are using what are called fish hook arrows. So notice the arrow looks like that. It just has a single side to it instead of like a double-sided arrow. And so we call it a homolytic. We're saying it's same because each atom gets the same treatment. So our bond is made up of 2 electrons. And so we're taking each electron and giving it to an atom. So the X gets an electron and the Y gets an electron. And notice that they're both still neutral. So let me show you why they would be neutral with an actual example here. If we have a CH3 bonded to a chlorine, and I'm going to break that bond, we're going to get a CH3 radical and a Cl radical. So if I'm going to write these out completely as a Lewis structure, just so we can see charges a little bit better, our carbon is bonded to those 3 hydrogens and has that radical electron. And if we do our formal charge calculation, we know that carbon likes to have, or it starts with 4 valence electrons. It has 3 bonds, and it has that 1 unpaired electron. So 4 minus 4, it's a neutral carbon. Now that doesn't mean to say that it's stable or unreactive. It just doesn't happen to have a charge. And then chlorine, we know that chlorine started with 3 lone pairs because that's what chlorine has. And now it has that radical electron. It starts with 7 valence electrons. It doesn't have any bonds, but it now has 7 electrons. So it is also neutral. Sorry, I don't know if you guys can hear that horrible beeping. I don't know if it's a garbage truck or what's going on out there. But we have 2 neutral atoms because that bond that they're sharing, when we count that for formal charges, we would count each atom as getting one of those electrons when they're sharing it. So in a sense, when we break it in half, the way we count it is the same. I don't think there's much else to say on here. We just have the difference of the 2 arrow types. And a reminder that that fishhook arrow is just showing us the movement of 1 electron. And then we have the movement of 2 electrons. So questions at all just on the kind of generic radical stuff there? Okay. Let's talk about some structure stuff then. When we talk about carbocations, we know that they're sp2. And when we talk about carb anions, we know that they're sp3. And the difference there is that a carbocation has 3 bonds, and that's it. So it has that empty space. It has an empty orbital, so it becomes sp2. But a carbanion has 3 bonds, and it has that lone pair, so it becomes sp3. It has four spaces, 4 things that need to go into orbitals. Carbon radicals are kind of in between. They have this unpaired electron, and so we can actually think of them as being trigonal planar, which would be sp2, or tetrahedral, which right here says shallow pyramid. So we know that a tetrahedral that has a lone pair in it would be trigonal pyramidal. So in that tetrahedral family, though, which would be sp3. And in reality, it's somewhere in between these 2, which I know sounds annoying and horrible. But remember, hybridization happens to make atoms, to make molecules more stable. And a part of it is electron repulsion. The electrons are pushing away from each other so they can be away from each other as much as possible. Normally, when we're talking about that, we're talking about pairs of electrons, either bonds or lone pairs. So a single electron doesn't have a whole lot of pushing power to push away the other bonds, the other electrons. And so it ends up in between these 2 states. And so really, we're just going to think of it and treat it as a trigonal planar shape. So trigonal planar and sp2. In reality, it's in between the two. But for thinking about reactions, for thinking about if we're going to attack from one side or the other side, we're going to treat it as a trigonal planar shape. It's neutral. We talked about that already. It does have an incomplete octet. So even though we have a neutral shape, a neutral atom, we only have 7 electrons going around it. So 6 for the bonds that it has, and then that lone pair electron gives us that 7th electron. So it does have that incomplete octet, which is why it's going to be so reactive. The last 2 bullet points here are similar to things that we've talked about with carbocations. The stability increases with substituents. So on the bottom here, the methyl group, so a CH3 radical, is the least stable. It's definitely a garbage truck. And the tertiary is the most stable. So having more substituents is going to increase that stability. And that's the same thing with carbocations. So I mentioned the carbocations. And then the last thing on there, it says that they can be stabilized through resonance. And we know that carbocations can be as well. These ones are, of course, a little different though. So that's what we're going to look at on a blank slide here so I can draw some stuff out for us. So we're going to look at 2. So we're going to look at an allylic radical, and then we'll also look at a benzylic radical, so next to a benzene ring. We'll start with allylic though. When we do arrows to show the electrons moving, whenever we're involving radicals, it just requires a lot more arrows because we have to draw an arrow for each electron instead of each pair of electrons. So here's how we're going to show that this has resonance, how we're going to show those electrons moving. We have to break the pi bond. And what we're going to do is we're going to take one of those pi electrons and put it right there. And then the radical is going to go right there as well. So those 2 arrows are showing the formation of a new pi bond. That pi bond was made up of 2 electrons though. So we have to show where that other electron is going to go. And it's going to go right there. So there's my new pi bond. It came from the radical electron and one of the pi electrons. And then there's our new radical location. And then this is resonance. So I'm going to put it in brackets there. Questions about the resonance there or anything? Okay, let's do one more then. We're going to look at a benzylic radical. And just like we've talked about with carbocations, because these have resonance, it makes them more stable. So if we have a primary allylic, that's going to be more stable than just a regular tertiary. So adding in that resonance is going to make it more stable than anything that doesn't have resonance, regardless of how many substituents it has. Okay, benzylic is going to be the same, just more of it because there's more double bonds. So we're going to start by just creating that new double bond. So from the radical and one of those pi electrons, and then the other pi electron just goes right there. So my first 2 pi bonds there didn't move, so I always draw those in first. My new pi bond is right here. And there's my new radical location. And then this is one of those things where we just kind of domino effect, keep going around the ring. So we're going to take our radical and move it right there. So we're splitting that pi bond up to make a new pi bond and a new radical. And then again, I'm going to draw the 2 pi bonds that weren't affected. They didn't change at all, so it's easy to keep them where they were. There's my new pi bond and my new radical location. And then we do the same thing. So radical, pi bond, radical. So there's my 2 pi bonds that weren't affected. Here's my new pi bond location and my new radical location. And we're almost back to the start. So now we're going to go right there. We're going to go there and there. Let's try that again. So there's all the stuff that wasn't affected, wasn't involved. Here's my new pi bond location, and there's the new radical location. So my brackets are going to look a little funny for this. Actually, let's just do big giant brackets like this. I was going to do little ones the start and the end, but that makes it a little more normal. So this has 5 resonance contributors. So just kind of a reminder, I know we've talked about this in earlier chapters, but it's been a while. Remember that first one and that last one, even though they look very similar, they're technically different resonance contributors because the location of the bonds in that benzene ring are in 2 different spots. They've rotated. So they do count as individual resonance contributors. So well, I'm not sure if the book asks about how many resonance contributors there are. That is something we talked about on earlier exams. But just a reminder that those do each count individually. Questions about the resonance? Okay. Mechanism patterns. So we know our mechanism patterns. We've been using them in multiple chapters. I draw a mechanism and ask you what pattern it fits with. We've done this many times. These ones are different because these ones are now mechanism patterns for radicals. And there's 6 of them. So there's 4 on this slide. There's 2 on the next slide. Yeah. So some of them involve breaking bonds, some are forming bonds, and some are kind of like a transfer thing happening. So we're starting at number 1, and number 1 is a homolytic cleavage. So we've seen this one on the first slide, but it's literally just breaking a bond. We have to have light or heat. So our triangle there is heat. That is light. So that's Planck's constant and frequency. So the Greek letter nu. Either one of those have to be included. That's what gives it the energy to break that bond. So you'll see one of those in most of the reactions we're going to look at. Number 2, addition to a pi bond. So 2, 3, and 4 are all creating new bonds and breaking a bond. So in order to make the new bond, an old bond has to break. So in number 2, we are breaking the pi bond, but we're going to form a new sigma bond. So it's written here as just an X. That doesn't necessarily mean a halogen. I know that's kind of our halogen symbol, but in this case, it really just means something. It means an atom. It means something generic. So we're adding a atom to a pi bond. And we've seen similar things to this when we've done heterolytic mechanisms. We know that our pi bond can act as a nucleophile. So this isn't hugely different, but it definitely has a different look to it. Number 3 is hydrogen abstraction. So we've definitely seen proton transfers, hydrogen transfers. Notice though, it specifically says not the same as a proton transfer. And of course, the reason why it's different is we end up with a radical. So we are breaking the bond between the hydrogen and whatever it's attached to. So we're breaking a sigma bond, hydrogen, to whatever it's attached to. And then we're forming a new bond between the original radical and the hydrogen. So the original radical becomes bonded to the hydrogen, and then we're forming a new radical. So new sigma bond. And then the number 4 is halogen abstraction. So it looks nearly identical to the one we just did. The difference is that we're focusing on a halogen and not a hydrogen. But in both of these, we're forming that new bond to either a hydrogen or a halogen, and we're also creating a new radical. All right, number 5 and then number 6. Number 5 and number 6 are reverse mechanisms of ones we've already seen. So number 5 is elimination. So this is the reverse of the addition. So let me go back and just remind you. So right here, we started with a pi bond and a radical, and then we combined them together. Number 5 is they're combined together, and now we get a pi bond and a radical. So we're taking that sigma bond, so this sigma bond right here, we're breaking it to make a new pi bond and our new radical. And then the last one is coupling. So this is the opposite of breaking a bond. So our very first one up here, number 1, we took that sigma bond and we broke it in half to make 2 radicals. Now we're taking 2 radicals and combining them together to make our new sigma bond. So these are our 6 steps. There's another way we can group them together. So here's our 6 again in little kind of mini versions. There's 3 words up here: initiation, propagation, and termination. So we're taking those 6 mechanism steps and we are putting them into these subcategories. And how they're categorized here is based on whether we start with a radical, we create a radical, or both. So let me show you what I mean. In an initiation step, we're going to start with 0 radicals, but we are going to make radicals. So the description there says that radicals are formed from non-radicals. So notice what we have here. We just have a regular bond between 2 atoms. So those are non-radicals. But in that reaction, in that homolytic cleavage, it's going to make 2 radicals. So in an initiation step, it's creating radicals from non-radicals. It's the only one that fits into that category. And then our propagation steps are all of these. So obviously most of them fit into this category. Propagation is we're going to start with a radical, we're going to change some stuff, and we're going to end with a radical. So when I hear the word propagation, I always think of gardening or plants. And if you take like a cutting of a plant, you take a leaf, you can propagate it, you can grow a new plant from it. And so in my head, that's how I think of this, is that we're starting with a radical and we're growing a new radical from it. We're propagating a radical. So let's look at one of these as an example. So right here, we have that X radical. As we form new bonds, we break bonds, we're still creating a radical in our product. Right here, our R, our carbon, has a radical. It forms a bond with that halogen, and then whatever was attached to that halogen is still going to be a radical. So we're keeping a radical in our solution, in our beaker. The last type is termination. And a termination is essentially the opposite of initiation. We're going to start with 2 radicals and we're going to end with no radicals. So we have our 2 radicals there. Because they're coming together to form that bond, we don't have any radicals when we end. So termination, we're ending the radicals, we're terminating them. So the words that are used here are also going to make sense as we look at one of our reactions, because we will label the steps as either initiation, propagation, or termination. And it helps to explain kind of the progression of the reaction itself. Questions about any of the mechanism steps, any of these labels? Okay. So we're going to look at our first reaction. And the way that this mechanism is laid out is it looks a little bit different than what we're used to seeing. First of all, the mechanism itself is different because we're using radicals, but it's just kind of laid out stepwise a little bit different. So I'm going to label this as reaction number 1. I don't think, okay, I do have them labeled as numbers in my notes. I can't remember if I have them labeled as numbers on the slides because I don't think the book does them that way. But we are going to call this guy reaction number 1. It is the chlorination of methane. So of course, I'm going to give this a little bit more of a generic reaction. So we're just going to say that we're going to start with an R group. So that can be any carbon group. We're going to react this with X. No, sorry. Let's get rid of that plus. We're going to react it with X2. And I'm going to put heat there. And we're going to end up with this. So really what we're doing is we're taking an alkane and we're going to attach a halogen to it. The X can be chlorine or bromine. And instead of heat, I'm going to just put or light. This is a super important reaction. We're taking an alkane, which we've normally said is very unreactive. We've said that you have to have a halogen attached to it, or an alcohol, or it has to have a pi bond, or an alkyne has to have a triple bond in order for it to react. We have to have reactive carbons or reactive sites. When we have an alkane, we don't have any of those. So this is essentially a way to create reactive sites or reactive carbons on a very unreactive molecule. And we know a whole bunch of reactions that we can do once we have a chlorine or a bromine on there. We can do all of our substitution reactions, all of our elimination reactions. So it's a really good starting point to then do kind of a chain or a multi-step synthesis reaction. So let's look at our mechanism for this. Notice the steps are labeled here. Our first step is an initiation step. So we're starting with our halogen. So we're showing it as Cl2. We're literally showing this with methane and Cl2 because we're showing the basics here. But we're starting with an initiation step. And so we're breaking that bond between our 2 halogens and creating 2 halogen radicals. So in this case, 2 chlorine radicals. The next 2 steps are both propagation steps. So notice the specific mechanism name is in the middle here. In that first propagation step, we're going to take that chlorine radical and we're going to remove a hydrogen from our alkane chain. So right here, I'm not going to draw over the arrows because they're a little small, but right here, we're using that chlorine radical, and then this bond right here between the carbon and the hydrogen, we're breaking that bond, and we're making a new hydrogen chlorine bond. And more importantly, we're creating a carbon radical. Next step, we're going to react it with another Cl2 molecule. So these are definitely not reacting in a 1-to-1 ratio, but remember, that's okay. We know that these are mixed together in a flask, and they don't have to be in a 1-to-1 ratio. So we can have more chlorine in there than our methane. But we're going to break, actually, let's just draw it on the molecule. We're going to break that chlorine-chlorine bond right here. And so when we do that, one of the electrons goes onto the chlorine to create a chlorine radical, but the other one creates our product. This is our final product right here. We're creating that carbon-chlorine bond, so our alkane is now bonded to our halogen. The other chlorine radical can then react with another methane molecule, because look at what we start with. We start with a chlorine radical. And so that's another reason why these are called propagation steps, because it allows it to go through this kind of like domino effect, or a propagation, where the product that we made, one of the products we made, can go back and keep reacting. So it allows for this cycle to continue to happen. Now, this isn't the end of the reaction, though. We also have termination steps. And termination steps are not necessarily wanted. They kill the reaction. So we have to have a continual radical in order for our product to form. So these steps are all destroying radicals. They're all coupling reactions, because remember, that was our only type of termination step we had. And really, a termination step can be any time we take two radicals and combine them together. So this is all of the radical types combined together. So on that last slide, we had chlorine radicals and we had carbon radicals. And so we could combine two chlorines together, we could combine a carbon and a chlorine together, or we could combine two carbons together. Now, some of these are good, some of them are bad, and some of them are just, doesn't really matter. If this one forms, this is good, because this is our product. It's not really the way that we want to make our product, because we've destroyed the radicals and haven't produced any new radicals in the process. So it essentially stops that chain of reaction, but it is our product. So this would be the best option. Up here, the two chlorines, that's kind of in the middle. It's not a horrible thing to have happen, but I'm going to go back up a slide. Right here, we know that if there's light or heat, those two chlorines can break back apart. So it kind of sets us back a step, but it's not the end of the world. We can make something out of it and continue with the reaction. The last one, though, is the bad one. So in this last one, when we combine those two carbons together, we're going to get a side product or a byproduct that we don't want. So this is an unwanted byproduct. So when we combine those two carbons together, it creates ethane. But what we're trying to make is chloromethane. So it's making this extra thing that is not part of our final product. Let me see. Okay. Questions about any of these reaction steps? I'm going to draw it out one more time on the next slide. We're going to look at something a little bit bigger. And I'm going to kind of combine it together a little bit better so it looks more similar to what we're used to seeing. But I'm looking at my notes here. Okay. All right, let's draw one out a little bit different. Let's see. So here's our problem. The question would say, draw all of the mechanism, electron pushing arrows, and final product. Okay. So I'm going to do a couple things here. I'm going to start with my 2 chlorines. So this is my initiation step. And a lot of times with this type of problem on a test, I will also have you label your steps. So label them as initiation, propagation, termination. So we'll add that on here. Label steps as initiation, propagation, or termination. So we're starting with our initiation step. We're breaking the chlorines. That's all that happens. I'm not going to show all of the electrons going around the chlorines. It's not necessary. I do need to draw in a hydrogen. So since we're doing that hydrogen abstraction in the second step, we need to show that hydrogen in there. So here's my propagation. I'm going to use one of those chlorine radicals. We're making a hydrogen chlorine bond, and then the other electron going right there. Not the prettiest arrow. There we go. So this is still initiation. This is still propagation. I'm going to take that new radical and I'm going to now react it with a Cl2 molecule. So I'm doing a halogen abstraction. So we're going to break that chlorine-chlorine bond. And there we go. There's our final product. So we've added a chlorine to one of our carbons. Now, I haven't shown any termination steps in here. So I'm just going to add in a termination step. Remember, we have a few different ones we can choose from, but I'm just going to show this one. So I've shown my initiation step. I've shown my propagation steps. Remember, this is our goal. This is our actual product. I know it can be a little confusing with this one because we're kind of showing it in pieces here, but adding that halogen to our carbon is the final product for this reaction. Any other questions about this one? Okay. The next couple slides are essentially looking at ways that we can start these types of reactions and then ways that we can prevent these reactions from happening. And when I say these reactions, I mean radical reactions in general. And so first, what we're looking at are radical initiators. So these are molecules that can go through that initiation step and then start the propagation step, start that domino effect. Because once we get one radical, it's much easier to go through those propagation steps and kind of start that domino effect and continue that radical cycle. So the first one we've already seen. We've looked at our chlorines. The next two, look at what they are. They're both peroxides. So we've seen oh, I just threw my stylus. We've seen peroxides. We've used them in our alkene chapter and our alkyne chapter to do a anti-Markovnikov reaction. And a lot of times it will just say like ROOR, and we've just kind of said it just needs to be a peroxide. So the two different ones that are on here are alkyl peroxides, which really just means it's a carbon chain, an alkyl group. And then the other one is an acyl peroxide. That's an acyl group. And it essentially means that it's a generic carbonyl kind of group. So it's a carbon-oxygen double bond with something attached to it. But what both of these have in common is they both have that oxygen-oxygen single bond. And what all three of these have in common is it's a weak bond. So that chlorine-chlorine bond is fairly weak, and then that oxygen-oxygen single bond is weak. They are both weak enough that they can be broken by just adding in some heat or some light. The heat and the light can then allow it to go through that cleavage reaction. And what we end up with is a halogen radical, or excuse me, two halogen radicals, or two oxygen radicals. So all three of these, the purpose is to create that radical so that it can then start those propagation steps and get the rest of the reaction going. Now, on the other side of it, we want to have radical inhibitors. So these are molecules that will prevent those propagation steps from happening or stop them from happening. One of them is molecular oxygen. So I know that this looks real similar to what we had on the last slide, but remember, molecular oxygen can also be represented as a double bond. And then the other one is hydroquinone, which is this guy. So both of these can go through a abstraction. So they're both hydrogen abstractions here, because what's happening is wherever the radical is that we have in our solution, it will grab a hydrogen. Let me add in, let me put the mechanism arrows in here. It will go through a hydrogen abstraction so that we end up with a radical on the oxygen. And that radical is resonance stabilized. I drew 4 different benzene-based radical structures a couple slides ago. This would have all of those radical resonance contributors. That's going to make it much less reactive. And so even though it has the radical, it's going to stop the rest of the reactions. It's going to stop those propagation steps from happening because it's much less reactive. And if that hydroquinone goes through that same reaction twice, so notice there's already a radical on the right oxygen, and now there's a radical on both of them. This is one of our resonance contributors, benzoquinone. And notice there's no radicals. Everybody's stable and happy. And we end up with a much more stable molecule. And so if it goes through that abstraction twice, it's definitely going to kill the reaction, kill the radical reactions, because there aren't any more radicals. It's reached a much more stable, much less reactive molecule. So these are used to quench a reaction, which is really just a fancy way to say stop a reaction. That they are also sometimes added into solutions if a solution is is unstable because of radicals. Sometimes these molecules are added in there to prevent them from breaking down or prevent those radicals from forming. Questions about the initiators or the inhibitors? To think of the right name there. Okay, just checking our time here. We're doing good. All right. Now, I already told you that we can do this first reaction. We're still looking at the first reaction, by the way, but I've already said that we can do that first reaction with chlorine or bromine. So the next couple slides, we're going to look at why those two work and why fluorine and iodine don't work. And honestly, it's the same reasons we always give, but this is just kind of putting some numbers to it and getting a little bit more specific. And we're looking at two things. We are looking at entropy and we're looking at enthalpy. And in the entropy up here, it says that there's really no change. We're starting with two molecules, so whatever our alkane is and our halogen, and we're ending with a haloalkane and HX. So our halogen with the hydrogen we took from the alkane. So we start with two, we end with two. So there's really no entropy change because the number of molecules and the state of the molecules is constant. So that takes us over to enthalpy, and we're looking at how much energy is needed or is given off when we break the bonds. So in the last column, so over here is the enthalpy for each of those reactions. So notice that for fluorine, it is negative 431 kilojoules per mole. So remember, negative means exothermic. So that's telling us that's how much energy is being given off when that reaction happens. That's a lot of energy. It's 4 times as much as chlorine. Because it's such a huge amount of energy, that really, again, means that it's pretty explosive. So we don't deal with fluorine very much. Chlorine is negative 104 and bromine is negative 33. So they're both exothermic, which means that it's both a favorable reaction and it's a reasonable amount of energy. And then there's iodine down here, and iodine is a positive. Oh, there we go. Iodine is a positive amount, so it's endothermic, which we already know. If something's endothermic, that means that it is not a favorable reaction. And so iodine is going to be a much slower reaction. So again, we don't deal with it. So this one is just too slow. So fluorine is too fast and too reactive, and iodine is just too slow. So we stick with the middle ones. We already know that chlorine and bromine are the good ones, the ones that can work. This is showing us those two main steps in our propagation and the individual energies for each of those. So let me add in some arrows here. We have the hydrogen abstraction. So this is our first propagation step. So we're going, oh, sorry, let me try that again. There's my new bond forming between my hydrogen and my halogen. And then the other electron goes onto the carbon as a radical. And then in that second propagation step, we're doing a halogen abstraction. So I'm going to form a new bond between my carbon and my halogen. And I'm going to put the other electron as a radical on my halogen. And so what the numbers are telling us here is that for chlorine, that first step is exothermic. For bromine, it's endothermic. And then for the halogen abstraction, they're both, oh my gosh, they're both about the same. They're both exothermic, almost the same number. It's just that first step is different for them. But overall, the net reaction for both of them is exothermic, meaning it's favorable for both of them. Now, here's one thing, though, that we're going to see in the next couple slides is because these two numbers are pretty different. I mean, one's exothermic and one's endothermic. Already that makes them very different. it means that bromine is going to be slower to react and chlorine is going to be faster to react. Now, why that's important is because bromine is slower, that means that it's going to be more selective. Let's see, I'm going to put this down here. So really what that means is that if we have a propane chain and we have two methyl groups on the end and a CH2 in the middle, and we're trying to decide where is that bromine going to add, because we have a CH2 group and we have CH3 groups to choose from, we know that the bromine is going to be more selective because it's going to want to create the most stable radical. So more selective, and it's going to be based off of, where are those lines coming from? It won't let me erase them either. I don't know what's going on there. It's going to be based off of radical stability. And then our chlorine, I also don't know why half that chlorine keeps erasing and then reappearing. Our chlorine is going to be more reactive, which really means less selective. And so what that means is that we will get more of a mixture of products. So I'm going to show you what that means on the next couple slides, but it's based off of those two numbers right there. It's based off of the fact that they have different energies in that first step. So here's the actual energy diagrams. So this is showing the two propagation steps. Chlorine on the left, bromine on the right. So this is our energy diagram. So we have energy on our y-axis, time, progression, however you want to think of it on the x-axis. So the activation energy that is labeled here on both of them is the first step, that hydrogen abstraction. So a couple things to point out. Obviously, bromine has a much larger activation energy. And so this is going to be much, much slower, and this is going to be much, much faster. The other thing to point out is that with chlorine, that first step is exothermic. So notice right here, there's our delta H for that first step. The delta H is negative. Right here, there's our delta H for our first step for bromine, and it's definitely a positive number. So we're creating something that is less stable than what we started with, and it's going to be a much slower process to get there. The second step, let me go back a slide for a second here. Right here, that second step is nearly identical in terms of the enthalpy change. And if we look here, there's our activation energy, there's our activation energy, and then we have our delta H and our delta H. So that portion of the graph, the second half of the graph, is very similar to one another. So what we're looking at, though, is the first half of the graph. Chlorine is going to be a much faster reaction because of stability and because of that activation energy. And bromine is going to be much slower because we're making something that's less stable, and it's going to be a much slower process to get there. So why we care about this, what this really means to us, is what type of product are we going to get? So on both this slide and the next slide, we're looking at reacting propane with our halogen, with some light or some heat. And the question is what products will we get and which one will be the major product. Whenever we have an alkane, we can have multiple products. Essentially, we can replace any hydrogen with a halogen. Now, I do want to point out one of the phrases on here. We're looking at monohalogenation products. So that means that we're only adding one halogen to our chain. We will talk about polyhalogenation, so usually just dihalogenation, but it is possible to add a second chlorine or a second bromine, but we're focusing on just one right now. Any hydrogen on our alkane chain can be removed and replaced with our halogen. And when we're deciding what our major product is going to be, it's based off of two things: statistics and radical stability. The statistics thing is, if we look at our products, so here is product number one. Product number one was made because one of these hydrogens was removed and replaced with a chlorine. Product number two was made because one of those 6 hydrogens was removed and replaced with a chlorine. If any of those 6 hydrogens is removed and replaced with a chlorine, we would get product number 2. So that means that for product number 1 to form, 2 out of the 8 hydrogens in that structure could have been removed to create the product shown. So 25% of the hydrogens. For product number 2, 6 out of the 8 hydrogens, or 75% of the hydrogens, could have been removed to create the product shown. So just based off of how many hydrogens there are in each location, we can't decide major and minor product, but it does give us an idea of how the balance gets a little bit shifted. The second thing we have to look at is radical stability. So for product number 1, if we take away one of those hydrogens, we're going to make that radical after that first propagation step. And if we do that with the other side, we're going to make that radical. Well, this is secondary and this is primary. So we already know that this one is going to be a more stable radical. We said that more substituents makes it more stable. And then our primary over here is going to be less stable. All right, so here's what all of this means. Let's wrap it all up into a nice little pretty package here. What it means is that whatever the more stable radical is, that's going to be our major product. So notice the percentages down here. It says that about 60% of the product is product number 1, and about 40% is product number 2. They are nearly equal. They're very close to being equal. But the one that came from the more stable radical will be the major product. One of the reasons they are so close to being equal is because even though the secondary one is more stable, there's only 2 hydrogens that were in the right spot to allow that product to form. The other one is less stable, but there were 6 hydrogens in that spot that allowed that product to form. So having that unequal balance of hydrogens almost balanced out the products. That's the moral of our story right there, though. So when we think about our generic reaction that I had on our first slide that looked like this, let's put an X there, let's be consistent. You can add on that the major is the more stable radical. Others will form. You will get a mixture of products with chlorine, but the major will be our more stable one. All right, so this is chlorine. What about bromine? Notice the percentage shifts. This is the exact same reaction we saw in the last slide, but now with bromine. With bromine, the overall story is the same. The major product will be the more stable radical. Bromine is much more selective than chlorine, though, because of that first step. So because bromine's first step is endothermic, it's going to be much more regioselective, so where the bromine adds. And so the major product will be the same, adding at that more stable radical, but those percentages are going to be drastically different. So with our chlorine, we're going to get a big mix of products, whereas with bromine, we get a very obvious major product and then a little bit of a side product. Questions about either one of these? Okay. Let me see, do I have? Oh, I wanted to throw in let me throw in a blank slide here. Okay, so here's what I want to do before we look at the next slide. Yeah, I don't have it. Okay, we'll do it here then. All right, here's our question. We're going to draw all of the products that are possible for this reaction, and we're going to circle the major product. So essentially what we're doing is we're attaching the chlorine to all of the carbons individually, individual products, and then deciding which one would be our major product. And we know that our major product is going to be based on radical stability. So here's how we do this. I'm just going to redraw my structure. And to create this product, we're taking away a hydrogen and replacing it with a chlorine. Well, we don't normally draw the hydrogens in, so that just means I'm going to add a chlorine right there. And I'm going to add a chlorine right there. And I'm going to add a chlorine right there. And we kind of keep going around. I definitely like to do this systematically and not just kind of pick random spots because it's easier to keep track of things. Chlorine there. And chlorine there. Do I need to also draw that one? I don't need that one because it is the same as this one that we already have over here. I'm going to uncircle that, but it is the same as that one. All right, so these are the 5 possible products that we would get from this reaction. We've just added a chlorine to every possible carbon because there's some symmetry in our molecule. We don't need to draw the chlorine adding right here and right here because that would be the same product. All right, the second half of this question is which one's our major product? I gave them numbers. 1, 2, 3, or 5. Did I skip number 4 when I said that? 1, 2, 3, 4, or 5. Which one is our major product? Which one do we think? Do we have a vote for 1? We have 2 votes for number 2. Another vote for number 2. The number 2s have it. It is number 2. The reason why it's number 2 is in order to get to that product, that is one of our intermediates. We would have a tertiary radical as one of our intermediates. Numbers 3, 4, and 5 would all have a secondary radical, and then number 1 would have a primary radical. So number 2 is definitely going to be our major product because it came from a more stable radical. Questions about that, about the products, about where the major product came from, any of that? Okay. So I think we have one more thing to talk about in this reaction. Stereochemistry. On the second slide, I said that when we have a radical, we're going to think of it as trigonal planar. And one of the reasons why we talk about that back in the beginning is when we look at how this reaction forms and we end up with a radical and then it's going to react with a chlorine, we need to know, is that chlorine going to approach from the front or from the back? Does it matter where that radical was to start with? And the answer is that we're going to get a racemic mixture. And so because we think of this as a trigonal planar atom, that means it's flat. And so our chlorine can approach from the top or from the bottom in equal amounts. So if we're creating a new chiral center, stereo center, asymmetric center, whatever phrase you prefer there, we will get a racemic mixture. So we're going to have equal amounts of our chlorine in the wedge and in the dash. And the other product that's listed here is adding the chlorine to one of those end positions. And that's not a chiral center. So it's not shown with any dashes or wedges there. So no stereochemistry for that one. If there was already a chiral center, so for example, in this structure, 1, 2, 3, 4, 5, 6, we have 3-methylhexane. Our methyl is on a wedge. It is a stereocenter. When the bromine adds to it, because we will get this as our intermediate, it loses its stereochemistry as that radical intermediate. And so now our bromine can approach from the top or from the bottom, and we will create a chiral center that is also racemic. So it's drawn here without any dashes or wedges, but we could fix that and we could put it like this and like that. So we would get a racemic mixture of our two products. And really with this one, if we were to draw all of the products for this one, we'd have a huge mix because the bromine could add there, 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 or there. So 5 other locations, and 3 of those locations would also create stereocenters. So there's 6, 7, 8. This would have 10 possible products if we include all the stereoisomers in our count. So it'd be kind of a mix, kind of annoying there. But long story short, racemic. So whether it's creating a new one or reacting at an existing one, it will be racemic when it's done. Questions about that one at all? Okay, let me see where we're at. So this is our second reaction, but I kind of don't want to quite start it yet because I don't want to stop in the middle of it. So let's call this our stopping spot for today then. And on Wednesday, we will start here. Lab today is one of our beyond labs, beyond labs experiments. So I will get you started with that. But I'll hang out here and answer any questions you might have. Oh, I remember the other thing I posted. I started telling you guys things I posted. The other thing was the exam reflection corrections. So if you haven't noticed that or seen that, it is up. I had to create like new assignments on Canvas for it. And it says that they're worth 0 points. So what I'm going to do is, so I already have, let's see, sorry, too many thoughts went through my brain there at once. What I'm going to do, or what my plan is, I'm not sure how well it will work, but what my plan is to have your exam corrections opened up on my tablet so that I can write on the screen, give you feedback, figure out how many points you get, and then have your original test opened up on my laptop so that I can kind of compare and see how many points you missed, because the points you earn back are based off of what you missed. And then you won't get any points in that exam reflection assignment. It will just stay as a 0. But what I'll do is I will change your test score. So if you got a 60 on the test and you earned back 10 of those points, I will change it to a 70. That will also help with keeping, like, whichever test gets dropped, it will keep all of that working out, right? Because Canvas does that for me. It does the figuring out which test is your lowest and dropping it. So that is my plan. We will hope that it works. But yeah, if you have any questions about that or any of the things I posted or about this chapter, I will hang out here. But I will see you at 10:15 in lab. But that's all.
Thank you.
Thank you.
Thank you.
Sorry, Professor, you said the max points we can earn are how many?
You can earn back 25% of the points that you lost.
Okay.
Yeah.
And you said between exam 2 and 3, we get to pick.
No, you can do both of them.
Oh, we can do both.
Oh, yeah.
Oh, okay, perfect. Thank you.
Yes. So I made 2 separate assignments. And so you'll just, after you do your corrections, you'll just take your pictures and upload them to whichever, either exam 2 or exam 3.
Got it. Thank you.
You're welcome. Professor, for the test reflection, do we only get points by getting the answer correct or by? No, you can also get points just for trying. So it's essentially, I'm going to grade it like I would a regular test question. So like, let's say the first one, you didn't write anything down. You missed 8 points. And then the second one on your exam reflection, I'll grade it just like I'm grading a regular test. So if you don't get the answer right, but you get, 5 points of partial credit because you're partway there, then that's how I'll figure it out. Does that make sense? Oh, I think oh yeah. Okay, you're welcome. Please go back to the slide right before 10.2. Do you want me to keep going, Gloria? Is it this one? One more. This one. This one. Is it that one, or do you need me to go one more? This one. That makes sense, since it's not on a slide.
I had a quick question. It has nothing to do with today's lecture.
Okay, I'm ready.
It has to do with last tests.
Oh, okay.
I know I'm very random. So for hydrogen formation,
Yes.
see, I'm taking it back. Does the alcohol add to the like, does it matter where the alcohol and like the bromine attach, or does the alcohol attach to the more substituted carbon?
Yes, it matters. And yes, the oxygen will attach to the more substituted carbon.
Okay, and then the bromine will, so it's more carbo.
It is. It is
For the
Markovnikov.
oxygen.
Yeah. And the reason why is because as the bromine carbon bond starts to break, it forms what we call a pseudo carbocation. So really, it's just like a really strong partial positive charge. And so that's what makes it Markovnikov, because we want that positive charge, that partial positive charge, to be on the more substituted carbon. And then the oxygen comes in and bonds with that carbon.
So does that one have carbon cation rearrangement?
It doesn't, because it never forms a full carbocation.
Oh, okay.
Because that the bromine bond doesn't fully break before the oxygen bond comes in, but because it has that like weird triangle shape, one of those bonds is just going to kind of start to break because it has so much angle strain. So it doesn't form that full charge, but it's definitely not a uncharged atom either. It has a strong partial positive charge.
Okay, and then for halogenation, like the bromination one,
Mhm.
that one, it doesn't matter because you're adding bromine to both ends of the
Correct.
double carbon, right? So
Yeah, if we were to show the mechanism for that one, it would be more accurate to show the second bromine adding to the more substituted carbon for the same reasons. But in terms of regioselectivity, we are adding either a bromine or a halogen to each carbon. So it doesn't really matter because they're getting the same thing.
oh, so for that one, it's not just bromination, it's called halogenation because it could have the chlorine too.
Yeah, we can do that one with bromine and chlorine.
Oh, okay, but not the other ones because they're true.
Yeah.
Okay.
Yeah.
Okay, sorry. I just want to clarify. Thank
Oh,
you.
it's okay. Yeah.
I'm trying to do that notebook. That's why I needed, since I didn't do well in the last test, I'm like, okay, I need to regroup my foundation.
The notebooks help a lot, and it does take some time, but I mean, part of that is helping you study. I mean, one of the things that helped me study in a lot of my classes, whether I was allowed to have a cheat sheet on a test or not, I kind of made one, and I would start by like summarizing an entire chapter per page, and then I would take, like, if there's 3 chapters on a test, I would take those 3 pieces of paper and rewrite it again, but so that it would only fit on one piece of paper, and then I would rewrite it again to fit on like half a piece of paper. So essentially I'm like rewriting all of the stuff that I found to be the hardest to remember or the most difficult, and then getting it down to like a note card size, and just by rewriting it I would remember it, and it made sense for me to do it that way, the repetition.
Yeah, it helps a lot. It helps me, like, I did it for like the first few reactions, and then I just like didn't keep doing it.
Yeah.
And then I was missing like little parts. Like I didn't write down, like when in the example I wrote, I just had bromine. So then I'm like, oh, okay, it's only this, but it's how it, okay, got it.
Yeah, and that is why I try to write them out generic, put R's and X's, and then underneath put down what that can mean, because it does help with your guys' reaction notebooks or your flashcards, because then you have essentially all the options.
Yes, thank you.
You're welcome.
So I had a more general question about like what part of well, let me backtrack. What type of questions you would ask from this chapter? Because I personally went over the chapter, but we didn't really have anything on the exam from this chapter. So I'm not really sure like what kind of questions you would ask. Like, would you want them to know the mechanisms, the patterns? What
So
else?
I do kind of just treat this chapter like the other ones, meaning that these will show up as box problems. So filling in products or missing reagents. There will be one of them probably as a mechanism on the test. And then they definitely play into the multi-step synthesis as well, because now we can just start a reaction with like propane,
Mhm.
and then that first step would be adding a halogen. Usually there with this, okay, so if we were in a normal teaching situation, I would normally have some multiple choice true false type questions on a test. Sometimes I include those, sometimes I don't, kind of depends on time. But for this one, like ranking radical stability or showing steps and asking what reaction or what mechanism pattern they are. Knowing the mechanism pattern names for this isn't as important to me though, so I probably won't include that. So, but radical stability would definitely be an important one to know.
Okay, sounds good. Thank you so much. And just to verify, your next exam is on Monday, right?
Yes, it is.
Perfect. Thank
Yeah.
you. See you next class.
Okay.
Bye-bye.
All right, Gloria, I see your chat there. What's your question for me?
On the exam reflection, it says that you can earn back 50% of the points.
Oh, did I say
you got.
50%? Okay, it is 50%. Sorry. I took a guess when Sajid asked me, and yeah, it's one of those things that when I typed it up, I went back and forth on what to offer. But yeah, if it says 50%, that's what I decided on.
Okay, thank you. I'm sorry to bug you about that.
No, it's okay. It's that if you didn't ask, it would be confusing. So I understand. And especially if Sajid's in lab, I'll make sure I mention it again, just because I don't want him to be confused either.
Thank you.
You're welcome.
Bye-bye.
Bye. Anything else from the rest of you? I think we're actually a little past time. I'm gonna do this and this. Any other questions for me? All right, I'm gonna go sign on to lab. I will see you over there.